And this is it. This is the solution to the second case. I have to drink something. It kind of hurts. And now we are going to take a look at the third case. And this is the last one and the hardest one. Good morning, fellow mathematicians. Welcome back to another video. This video right here is long overdue. I wanted to record this for like a year now, as soon as I started my differential equation playlist. The thing is, I tried recording this piece of crap so many times, but I just wasn't satisfied at all whenever I filmed it. So here it goes, and I hope it turns out okay this time. And this thing right here is pretty much the only reason why I started this differential equation playlist. And after that I can hopefully come back to doing more differential equation stuff. And after that we can probably continue with physics, because what we are going to talk about today is one of the most important cases in classical mechanics, for example, that you are going to encounter. Whenever you are not dealing with partial differential equations, you are probably going to end up with this thing right here. This is a second order linear differential equation with non-constant coefficients and inhomogeneous. What we are going to do today, we are going to assume that our coefficients are indeed constant. Otherwise things would get really pretty fucking messy. And also we want this to be a homogeneous equation, meaning we want this to be equal to 0. Okay? Meaning our differential equation at the moment turns into a times the second derivative of y plus b times the first derivative of y plus c times y in itself being equal to 0. And I'm not going to talk about really abstract stuff right here. And you can advance this idea to nth degree linear homogeneous differential equations with constant coefficients. You can make this arbitrarily large. The only real thing that is going to bother you in the end is that you have to solve, for example, a quintic polynomial, which is not trivial in a normal case. I tell you this, my Galois boys out there, it's not too trivial. Symmetries won't hold here. At first, I would like to make use of the ansatz we have talked about before. Meaning, we are going to give this thing right here a new name, this y. Let y be equal to c, where c is some complex constant, we don't want it to be equal to 0, times e to the lambda t. Y is with respect to t right here, okay? So this is our time-dependent function, you could say, if you are a physicist. If we differentiate this once, we are going to get c times lambda e to the lambda t, and differentiating this a second time is going to leave us with c times lambda squared e to the lambda t. I hope you agree with me that this is true, differentiating with respect to t. All that we really have to do now is plug this stuff into here and see what we get. Now, we are going to get, one thing I would like to do, we don't want those coefficients to be equal to 0 at the moment, without any restrictions. If one of those is 0, the whole thing is going to be a special case. So why not divide both sides by a right here? We're going to get y double prime plus b over a times y prime plus c over a times y. And we're going to give this b over a and c over a new name. So this is now y double prime plus, let's say this is gamma times y prime. I'm going to put it in a physics form, you could say, plus omega squared. Most of the time you're going to find this, it really doesn't quite matter, times y being equal to 0. Okay, we are going to put it like this. This is without any units, so we really don't care about units right here. Now we can plug our y in there. And I want you guys to notice whenever we plug this in, c times e to the lambda t is a common factor on all of those. So we are going to factor this out. Now we are going to get c times e to the lambda t. And you can only factor it out if none of those is equal to 0. Okay? It only works like this. And then we have lambda squared plus gamma times lambda plus omega being equal to 0. Like I said, this is not equal to 0, and a product of two things is 0 if and only if the one part is the first part is equal to 0 or the second part is equal to 0. This can't be equal to 0, so this is bound to be equal to 0. Meaning, this implies that lambda squared plus gamma times lambda plus omega must be equal to 0. And we can solve this easily by taking a look at a quadratic formula. Meaning, the two solutions, our roots of lambda, are going to be, okay, negative gamma over 2 plus minus square root of gamma squared over 4 plus, okay, this is going to be negative omega in the end. And this is what we have at the moment. Physicists like to do some stuff which makes things easier. For example, they put a little 2 in front of the gamma right here. This makes stuff a little bit easier. And also they like to put omega squared right here just for the dimensional analysis. Then you are going to get something that has the same units right here. But we really don't care about this. The only thing we care about are the 3 cases that we can actually encounter now. Okay, so there are 3 main cases that we have to take a look at. And there are physical words for that too, but I don't want to go into detail about that. This thing right here is actually then the solution to the undamped harmonic oscillator. Okay, no, this is actually the damped harmonic oscillator, the damped harmonic oscillator. It really depends on your solution then, but here, in general, it's the solution for the damped harmonic oscillator. Now we have 3 cases to consider, and they all have to do with the discriminant. If you ever did nonlinear dynamics, then you had to do so much stuff regarding this discriminant. All of chaos theory and nonlinear dynamics has something to do with the Jacobian determinant and plugging those discriminants in. It's kind of annoying sometimes. So 3 little cases. We can have that our discriminant is positive, that would be good. So our case 1 would be that gamma squared over 4 minus omega is greater than 0. We can have the case that gamma squared over 4 minus omega is equal to 0. Okay, this is the second case. And we can have the third case, the worst case you can say. We have that gamma squared over 4 minus omega is less than 0. And you might have guessed, this is going to give us complex solutions to this whole thing. But we said that our C's right here and later our superposition of those solutions is going to give us complex coefficient, and this is going to make things way easier. We are going to have a real fundamental solution in the end. And we are going to take a look at all of those cases one after another. It's going to take a while. There are probably going to be some bonus videos out on my second channel then. See you soon. So the first one is pretty easy. We are basically already done. So if you take a look at my superposition principle video and also my linear homogeneous differential equations of the first order video, then you might notice that we can actually put homogeneous solutions together to get ourselves a fundamental system, a fundamental solution, an auxiliary equation, meaning we can construct our y with respect to t as nothing but 1 solution C1 times e to the lambda 1 times t, and then plus C2 times e to the lambda 2 times t. Okay, this is how we are going to construct our fundamental system. And now it's just a matter of plugging stuff in. And well, there's no real problem with this right here. Whenever our discriminant is greater than 0, this is just going to be some real number. We can, for example, call it omega naught. Okay? This thing right here, our root, is just omega naught. Meaning, at first we are going to have some constant C1, real or complex constant. Let's choose it to be real, for example, we really don't care. E to the negative gamma over 2 plus omega naught times t plus C2 e to the negative gamma over 2 plus negative omega naught times t. Okay, don't mix your signs right here up. And well, what you can now basically do, you can distribute this t into everything, and you are going to notice that you have the same common factor e to the negative gamma over 2 times t. So we can bring it to the outside, leaving us with e to the negative gamma over 2 times t c1, e to the omega naught times t plus c2 e to the negative omega naught times t. One little thing that I would like to consider just talking about it, if our c1 and c2 are actually equal. So let's say we have a special case. c1 is equal to c2 is equal to some big constant c. Then we are going to have that y of t is nothing but this constant c, e to the negative gamma over 2 times t. And then we are going to have e to the omega naught times t plus e to the negative omega naught times t. And this thing right here is pretty cool. We had this solution to the rope sliding off a desk differential equation thing. If you take a look at the hyperbolic cosine right here of x, it's going to be nothing but e to the x plus e to the negative x over 2. You can multiply both sides by 2, and you're going to notice that this thing right here in parentheses is going to be 2 times the hyperbolic cosine of omega naught times t. And this is pretty cool, and 2 times the constant c is nothing but, for example, our amplitude. And then you are going to have a damped hyperbolic cosine wave, you could say. Okay, this has been our first case. This basically right here is our solution to this first case, and now we are going to take a look at the second one. One thing I totally forgot to mention is, if you really want to write out this auxiliary equation, you have to take for 3 things actually. You have to plug those particular solutions in, so the c1 times e to the lambda 1 times t into your original equation that you had, and you would have to check, you have to make a little proof, if this thing right there is seriously a solution to this differential equation, you would have to do this to the second particular solution that you had, and then also to the fundamental system that you had. Okay, in normal case you would have to make a little proof, you would have to do a little showing that those are indeed solutions, but you can trust me on that, they are indeed solutions to this problem. Let us move on with the second case. Our discriminant is equal to 0, meaning overall that our gamma squared over 4 is equal to our omega that we have right here. The thing about a root of 0 is that the square root of 0 is just 0, meaning we are going to end up with negative gamma over 2 plus minus 0, which is nothing but negative gamma over 2. And here's where the real problem comes in, because now you see lambda 1 and lambda 2, our 2 roots to this fundamental polynomial, are equal, and this is not good. If you have solutions to differential equations, they have to be linearly independent, meaning those roots can't be the same. So we have to do some little trickery, and when you do this, you really should show that this solution that we are going to get, that we are going to craft ourselves, is seriously a solution to this differential equation, and this is where the bonus video probably comes in if I make one. Meaning, okay, we are going to take a look at the first solution. So y of t can be constructed as c1 times e to the lambda, so our 2 roots are the same, lambda times t, and now we are going to do some black mathematics and say our second solution is nothing but c2 times t times e to the lambda t. Okay? This is actually the fundamental system, our auxiliary equation, and this thing is the solution to this case. It does work out. Take a look at the bonus video to see that this thing right here is actually a solution to our differential equation. I'm terribly sorry. My throat is itching a little bit. Meaning, once again, we can plug our root into here, and you can see at a glance that e to the lambda t is indeed a common factor, leaving us with a solution that this is e to the negative gamma over 2 times t times c1 plus c2 times t. And this is it. This is the solution to the second case. I have to drink something. It kind of hurts. And now we are going to take a look at the third case. And this is the last one and the hardest one. Here it goes. At first, little observation. Our discriminant is going to be less than 0, meaning this is, for example, -3. Okay? Square root of -3, whenever one part in the discriminant is greater than 0, 3 is greater than 0 if you trust the Peano axioms, then you can break this up into the square root of -1, which is I, times the square root of 3. Meaning, we can say that this thing right here is nothing but square root of -1 times the square root of, see, we have factored out -1, so this gives us omega minus gamma squared over 4. Okay, we're going to call this thing right here omega naught once again. I really don't care. This thing right here is going to evaluate to I, and this thing right here is just, as always, our little damping factor, you could say, that we are going to get in the process. Meaning, we can construct our y of t as being nothing but, okay, once again, our complex coefficients right here, and this time it's really important to have complex coefficients right here, okay? It's really damn important to get a real fundamental system. So we have C1, e to the lambda 1 times t, plus C2, e to the lambda 2 times t. We can plug this stuff into here. So we are going to get C1 times e to the, okay, negative gamma over 2, and then we're going to get plus I times omega naught times t, and then plus C2 e to the negative gamma over 2 plus I times, negative, or once again I mix it up, negative I times omega naught times t. Once again, we are going to get this damping factor as a common factor. That's a cool thing that you are going to get all the time. So this is going to give us e to the negative gamma over 2 times t. And then we are going to get C1 e to the I omega naught times t plus C2 e to the negative I times omega naught times t. And now, here comes the worst part, you could say. What we are going to do, we are going to break this up using Euler's formula. We have talked about this before. E to the I times x is nothing but the cosine of x plus I times the sine of x. Okay? We are going to get e to the negative gamma over 2 times t, and then we have C1 cosine omega naught times t plus I times the sine omega naught times t. For the second part, plus C2 cosine of omega naught times t, in normal case negative omega naught times t, but the cosine wave is an even function. Yeah, right. I seriously had to think about if it's called even in English. Why even did I put a thought into this? Never mind. And on next part we are going to get plus I times C2. In this case, I forgot the C1 right here. Okay. And then we are going to get the sine of negative omega naught times t, but the sine of negative x is negative the sine of x. So let's bring the negative sign to the front, and we are going to get the sine of omega naught times t. And this is pretty much some beautiful symmetry, you could say. We can collect terms overall. So this is e to the negative gamma over 2 times t times, okay, on the cosine part, we are going to have C1 plus C2. And on next part we have this common factor of I plus I times C1 minus C2 times the sine of omega naught times t. Okay? This is pretty dope, and the cool thing is a constant plus another constant is just another all constant. Let's call C1 plus C2 capital A for amplitude, for example. And now we said that our coefficients are complex, so I times C1 minus C2 is just yet another new constant. We are going to say that I times C1 minus C2 is nothing but some other constant, capital B for example. And this is pretty cool. We are basically done with this then. Meaning we are going to get y of t is nothing but our damping factor. And then times. We're going to get a times the cosine of omega naught times t plus b times the sine of omega naught times t. And if you are real badass, you can do some trigonometry in the phase space of this thing right here, and you can collect the terms even more to get a damped wave, a damped cosine or sine wave. It depends on your parameterization, with a little phase shift factor in there. But I'm going to talk about this once I do a bit more Laplace transforms of physical systems. I thank you guys for watching. If you did enjoy this video, please like, subscribe and recommend the channel if you like. This turned out better than expected. This right here is our fundamental solution of the complex case, and it turned out pretty nicely. If you want to support the channel a bit more, buy those great Euleroy t-shirts I created. They are seriously cool. Or support the channel on Patreon. Take a look at my second channel where the bonus video is going to be. And up until the next video, I'm wishing you guys a damp day, I guess. See ya.
Es ist nicht schön, wenn irgendwo zu viel in irgendwas Kleinem steckt. Das kann sexy manchmal sein bei Busen, aber bei Fuß ist das nicht so schön.
Ich würde beinahe sagen, Fuß will eine Nummer größer sein.